In the last lecture, we analyzed a dynamical system of foxes and rabbits in which we assumed that the system progressed in discrete time steps. So we spoke of populations at time 1, time 2, time 3, but never in between. In some cases, discrete time steps make sense. For instance, if there's a mating season for foxes and rabbits, then maybe we can only take a census of populations once a year. For this discrete dynamical system, we wanted to predict a sequence of populations as time moved forward. However, many dynamical systems proceed continuously. In such cases, the quantities of interest change over time, and we are interested in knowing what those quantities are at any given time, not just integer time units. For instance, consider a mass hanging from a spring, and suppose I stretch it and let it go. How will it behave? In asking this question, I want to know what the spring is doing at each point in time, not just at whole number of time units. In other words, I want a function of t as an answer to my question. If z is the vertical height of this spring, what is z as a function of time? If we know something about the rate of change of functions involved in a continuous dynamical system, then we can often use the subject of differential equations to study such dynamical systems. I'm not going to assume you know any differential equations, but I'll assume you know just a little bit of calculus. And even if you don't know calculus, you may be able to follow the general thread of this lecture, since I'll try to explain the ideas of calculus in a friendly way. Calculus helps us understand rates of change of functions over time. So if you have a function f of t that depends on time t, the rate of change of the function with respect to time is a new function that also depends on time. We call it the derivative of f, and we usually write it as f prime of t. Sometimes when referring to the derivative, we just omit writing the time parameter and just say f prime. For instance, f of t could be the position of a car at time t. The rate of change of position of the car may also change with respect to time, so it is a function. We usually call that the velocity of the car. And there's a lot of effort spent in a calculus course to learn the derivatives of various well-known functions, like polynomials or exponentials or other things. When you have a physical problem that involves a rate of change of a function, it places a condition on that function's derivative. This is what's called a differential equation, or sometimes we say dE for short. The dE might be a condition like this: f prime of t equals 2f. The solution to a differential equation is a function that satisfies this given condition. If you took calculus, you might know a function that satisfies the condition in this example, that the rate of change is proportional to the function. If you think about it, such a function must be growing very fast. In fact, faster and faster as the function size gets large. It makes sense then that exponential functions satisfy such conditions. In this case, f of t equals e to the 2t is a solution to the differential equation f prime of t equals twice f of t. More generally, if x of t is a function that satisfies x prime equals a times x for some constant a, then a solution is x of t equals some constant c times e to the at. Now, an amazing thing is that this exponential solution, in some sense, is the key to solving lots of very complicated systems of differential equations. Let's look at another population model, this time a continuous model. Suppose we want to model the population of mice and rats in some ecosystem. Mice and rats are similar and they compete for resources. Let's model the populations over continuous time, not discrete time intervals like we did with foxes and rabbits. There's nothing wrong with trying a discrete model to study this problem, and you might think about how it would differ from what we're about to do. Remember that when you create a model, you make choices that seem to make sense for the problem at hand. Maybe a continuous model makes more sense for mice and rats because they breed year-round rather than in specific seasons. So you'll be interested in their populations at any time of the year. Also, so that we can talk about rates of change, we'll assume that the number of rats and mice are not necessarily integers. This seems silly, but for large numbers of rats and mice, it's a reasonable assumption. Remember, we set up models to give us insight even if they aren't completely describing the situation at hand. So consider this model. Let x1 of t represent the population of mice at time t, and let x2 of t represent the population of rats at time t, where t is, say, measured in years. The rates of change of these populations depend on each other, and maybe depend on what resources there are available in the environment. Suppose, in the absence of rats, that mice reproduce at a yearly rate equal to 3 times how many there are. But when there are lots of rats around, they eat a lot of the food that mice eat, so the rate of mice reproduction is negatively impacted by, let's say, a rate equal to twice the number of rats that exist. Then we can set up a differential equation to describe this. We'll set x1 prime, the rate of change of mice, equal to 3 times x1, the number of mice, minus 2 times x2, the number of rats. Similarly, suppose rats grow at a rate equal to 4 times their number. That would suggest that this ecosystem has lots of yummy rat food to consume. But because mice eat some of the food that rats eat, rats are negatively impacted at a rate equal to the number of mice that exist. This suggests a differential equation for the rat population that says that the rate of change of rats, x2 prime, is equal to minus x1 plus 4 x2. What we have here now is a system of differential equations, a system of DEs, we sometimes say for short. System just means that there is more than one DE. And the derivatives of x1 and x2 depend on x1 and x2 in a linear way. It's for this reason that the DEs themselves are called linear differential equations. So is there a way to take advantage of the linear algebra that we've learned? Let's express this differential equation in a compact form. Let's let the vector x of t be the vector with components x1 of t and x2 of t. Notice the components are functions, so the vector is going to change over time. So we can talk about the vector's rate of change. We'll just take its derivative to be the derivative of the component functions. Then the system of differential equations that came from our model can be expressed as an equation by saying x prime equals a matrix A times the vector x. The matrix A has entries 3, minus 2, minus 1, and 4, and these are just the coefficients from our model. You can check that the matrix A has eigenvalues 5 and 2. An eigenvector corresponding to 5 happens to be minus 1, 1. An eigenvector corresponding to 2 happens to be 2, 1. Do these have any meaning for us? To investigate, let's look at a system of differential equations more generally. What we're looking at is a system of differential equations of the form x prime equals ax, where x could be a vector. Just to keep things simple, I'm going to assume A is a 2 by 2 matrix, but everything I'm going to say will generalize readily to any square matrix. So you could study a system of n linear differential equations if you wanted to. How can we solve the equation x prime equals ax? Well, we got to start somewhere. So let's ask, for what matrices would this system of equations be easy to solve? If you think about it a moment, you may realize that if A is a diagonal matrix, we can do it very easily. Look at this example of a 2 by 2 diagonal matrix with lambda 1 and lambda 2 on the diagonal. In this example, the two equations decouple. The function x1 prime will have no relationship to x2, and x2 prime will have no relation to x1. And each of them is a DE we've seen before, in which the rate of change of a function is just proportional to the function itself. We know the solution. It's exponentials. So if x1 prime equals lambda 1 times x1, then x1 of t equals some constant c1 times e to the quantity lambda 1 times t. You see, the exponent has the rate lambda 1 in it, and that comes from the proportionality constant in the dE. Similarly, x2 prime equals lambda 2 x2. So that means if you solve the differential equation, x2 of t equals some constant c2 times e to the quantity lambda 2t. The constants c1 and c2 here are arbitrary. This just expresses the idea that lots of functions will satisfy this differential equation. But if you have some initial conditions on the mice-rat populations, then you'll be able to specify these constants more precisely. We can rewrite these solutions as a vector equation. X of t equals c1 times the vector 1, 0 times e to the lambda 1t plus c2 times the vector 0, 1 times e to the lambda 2t. That's really nice. That's a very general solution to this system of DEs when the matrix is diagonal. You see, diagonalization in this case corresponds to decoupling the equations from each other. So what if the matrix is not diagonal? What's the next best thing we could hope for? You guessed it. If the matrix is diagonalizable, then maybe there is a way to solve this system easily. If you think back to what diagonalization has done for us, you'll remember it gave us a good basis of eigenvectors, and this basis was a more natural way to understand the action of the linear transformation that A represents. In other words, it was a good change of basis. And in our case, we'll also perform a helpful change of basis to turn the problem into the diagonal case that we just solved. So if A is diagonalizable, then we know A equals PD P inverse for some diagonal matrix D and invertible matrix P. So x prime equals AX becomes x prime equals PD P inverse times x. If I multiply both sides by P inverse on the left, I'll get P inverse times x prime equals D P inverse times x. Now, a good substitution may become apparent. If I set the vector W equal to P inverse times x, then this equation is going to simplify. It's going to be really convenient. Since P is a matrix of constants, taking the derivative of W is just going to be P inverse times x prime. You may have to think about that, but it's very similar to what happens for regular functions where you have constant times x and you take the derivative, it just gives constant times x prime. But this change of variable now turns the dE into one where the left side becomes W prime and the right side becomes D times W. So W prime equals a diagonal matrix D times W. We know how to solve this. Our method earlier shows us W equals this expression, where lambda 1 and lambda 2 are eigenvalues of A, and C1 and C2 are arbitrary constants. So we've solved for W. Hooray! But it's a little premature to celebrate, because we weren't interested in W, were we? We were interested in solving for the vector x. But since W equals P inverse times x, then x equals P times W. Now notice W is a vector written as a linear combination of vectors. So when we multiply on the left by P, we can just multiply P times each term. Also remember, P has the eigenvectors of A in its columns. So when you multiply P times the vector 1, 0, you'll just get the first column of P. When you multiply P times the vector 0, 1, you'll get the second column of P. And these are just the eigenvectors of A. So what you see is the population vector x is just a linear combination of eigenvectors times exponential functions related to the eigenvalues. This is a very general kind of solution when you have a diagonalizable matrix A. For larger square matrices, you would just have more terms, and you'd similarly use a basis of eigenvectors. All right, so what does this mean for our mice-rat population model? Well, using the eigenvectors and eigenvalues, we will get this general solution. Spend a moment studying it. What I want you to notice is the exponentials e to the 5t and e to the 2t. These came from the eigenvalues. The e to the 5t term grows much faster than e to the 2t as t goes to infinity. So that term, with the eigenvector minus 1, 1, will eventually dominate. The negative 1 in that eigenvector is paired with the mice population, but there's also a constant C1, which could be either positive or negative. If you look at the expression for the populations, you'll see that depending on the signs of the constants, the mice and rats might thrive or they might go negative, by which we interpret to mean extinct. The constants C1 and C2 can be found using given initial conditions if you have some. So for instance, suppose both mice and rat populations are both 300 at time t equals 0. Then if you plug in t equals 0 to the general solution, you'll get the vector with entries minus C1 plus 2C2 and C1 plus C2. This must be the population vector 300, 300. So solve for the constants and you'll find C1 equals 100 and C2 equals 200. In that case, the general solution becomes this specific solution. Then the mice population is minus 100 e to the 5t plus 200 e to the 2t. And you see that the negative first term will eventually outweigh any positive contribution from the second term. So the mice will eventually go negative, in other words, go extinct. We can see this qualitatively from just the form of the solution. The rat expression, on the other hand, is always positive and will grow indefinitely. And for any other initial condition, you might wonder what the signs of the constants will be. If you give it a little bit of thought, you can show that the constant C2 will always be positive as long as both populations are positive. I'll let you try that yourself. But if you grant that C2 is always positive, then the key question is, when is C1 bigger than 0 or less than 0 or equal to 0? If C1 is positive, the mice will go extinct and the rats will thrive. If C1 is negative, the rats will go extinct and the mice will thrive. And what we learn from the form of the solution is that there's a middle ground where C1 equals 0, where both populations will thrive. For what initial conditions will this happen? Well, looking again at the general solution, you can see that if C1 equals 0, then there's only the second term, and because of the second eigenvalue, the populations will be in the proportion of 2 mice to 1 rat. This is the critical ratio. If you have more than 2 mice to 1 rat, you can show that C1 will be negative, so mice will thrive and rats will go extinct. And if you have less than that critical ratio, you'll get the opposite outcome. There is some rich behavior for the solution to this system of linear DEs, and you should marvel at how we were able to find it from knowing the eigenvectors and eigenvalues of the matrix A. Let's look at another example, the mass spring system we started our lecture with. Recall that we were interested in understanding the motion of the spring. Well, if you think about it, you can probably guess how the spring is going to move if you pull it and let it go. It's going to oscillate, right? Well, that depends a little bit on how much friction there is, right? If we had a lot of friction, it wouldn't necessarily oscillate at all. So let's see how and when oscillation would arise. Let z of t be the position of the mass where z equals 0 is the equilibrium position. You may recall that the derivative of position, z prime, is velocity, and the second derivative of position, z double prime, is acceleration. We can analyze the total forces on the mass. There, the spring exerts a so-called restoring force that is proportional to the displacement and pulls opposite the direction of the displacement. So the restoring force is minus k times z for some positive constant k. Also, there is a frictional force that is proportional to the velocity and opposite in the direction of velocity. So that force is minus c times z prime for some positive constant c. Then we'll use Newton's law to write the total force as mass times acceleration, setting that equal to the sum of the restoring force and the frictional force. Let's study a specific example of such an equation just to get a sense of what is going on. And you can tackle the general equation yourself by taking a DEs course. But my purpose here is just to give you a taste of how linear algebra shows up. So suppose m equals 1, k equals 5, and c equals 2. Then z double prime equals minus 5z minus 2z prime. Let's try to solve this, assuming we pull the spring out to position 12 and then let it go with no initial velocity. Then z of 0 is 12, and z prime of 0 equals 0 will be our initial conditions. This is a differential equation that's unlike what we've seen before because it involves a second derivative. We call such a DE a second-order DE if it has a second derivative in it. We've only seen first-order DEs. However, we can actually turn this second-order DE into a system of first-order DEs by making a clever substitution. Let's let the derivative of z be a new variable, which we might as well call v for velocity. So z prime equals v. Then the original DE becomes v prime equals minus 5z minus 2v. And together, these are a system of first-order linear DEs. In fact, as you can see, the vector z prime v prime equals a matrix A times the vector z v. The matrix A has entries 0, 1, minus 5, minus 2. Then if we let x be the vector z v, then just like before, we have an equation. X prime equals a times x. So we should be able to solve it, right? Recall the general solution of this system is a linear combination of eigenvectors times exponentials involving eigenvalues, like this. And already we may be a little suspicious about whether this is really a solution because a springy spring's oscillatory behavior doesn't seem like it behaves like an exponential. But let's just keep going on. What we find when we calculate the eigenvalues is that the characteristic polynomial is lambda squared plus 2 lambda plus 5. And this has no real roots. If you use the quadratic formula, you'll find you'll need to use the square root of -1, usually denoted by the letter I. Turns out you get a pretty good number system if you include I. These are called the complex numbers. A complex number has the form a plus bi for some real numbers a and b. We won't need to say much more about complex numbers here, though there's a lot more you could learn about them. So if you try to find eigenvectors for complex eigenvalues, you'll discover their entries will be complex numbers too. If you just plow ahead and try to plug these things in the general solution, you'll get this expression, which we mark with a star so we can refer to it later. At time t equals 0, this solution becomes the vector z of 0, v of 0, which equals this expression. If you use our initial conditions and set z of 0 equals 12 and v of 0 equals 0 and solve, you will find the constants c1 and c2 to be complex numbers as well. c1 equals 3i and c2 equals minus 3i. We'll use those constants in the equation star. You might also notice that equation involves exponentials of complex numbers. We'll use an identity known as Euler's formula. E to the I theta equals cosine theta plus I sine theta. Then e to the 2it and e to the minus 2it can be expanded like this. Notice that we are beginning to get a clue for where the oscillation in the spring comes from. The exponentials of complex eigenvalues, because of Euler's formula, lead to linear combinations of cosine and sine expressions. Now I'll just say if you persist and write out everything carefully from here, I know equation star looks like a mess, but a lot of simplification happens. In the end, believe it or not, all the imaginary parts of the expression cancel and you get a real function, which is what you expect. Then we have z of t equals e to the minus t times the quantity 12 cosine 2t plus 6 sine 2t. Now it's quite amazing all this worked out. And there are other ways to try to get a solution, which are covered in a differential equations course. But this analysis we did taught us some things. If you are paying attention to where those terms came from, the exponent minus t came from the minus 1 as the real part of the eigenvalues. The 2t in the cosine and sine terms came from the 2 in the imaginary part of the eigenvalues. This suggests when there are imaginary parts on the eigenvalues, you will have some oscillatory behavior, and otherwise you won't. And if you look even closer at what we did, if you increase the frictional coefficient, you see the net effect of that in the quadratic formula is to make the expression under the square root more likely to be positive, so that you don't end up with a complex number. So that makes sense as well. Let's close our lecture by examining the behavior of matrices with complex eigenvalues. What kinds of linear transformations are they? For instance, in a 2x2 with no real roots, that means the matrix has no special directions in the plane that stay the same under multiplication by A. What kind of linear transformation is that? Well, a rotation is such an example. You might recall that a 2x2 rotation matrix is always of this form: r cosine theta minus r sine theta, r sine theta, r cosine theta. If you let A equals r cosine theta and B equals r sine theta, then you could recognize a rotation as being of this form as well: A minus B, B, A. Notice the action of this matrix is to send the standard basis vector 1, 0 to AB and 0, 1 to minus BA. So you can see that this is a rotation. And if you calculate the length of the vector AB, you'll get r. So it does send the unit vectors to vectors of length r. So it's also scaling by r. So if you start at some point and apply this matrix over and over again, what happens? Well, three things can happen depending on whether the scaling factor r is 1, less than 1, or greater than 1. If r equals 1, you just get a series of dots that move along a circle. Each time the angle from the origin changes the same amount. And if r is less than 1, you'll get a series of dots which spirals in towards the center. As before, the angle from the origin in each case changes the same amount. And if r is bigger than 1, you'll get a series of dots which spirals away from the center. And as before, the angle from the origin in each case changes the same amount. Now let's determine the eigenvalues of the matrix. If you subtract lambda off the diagonal and take the determinant, you'll get the characteristic polynomial a minus lambda squared plus b squared. The roots turn out to be a plus or minus bi. These are the two eigenvalues, and they're both complex. It is a fact that complex roots of any polynomial always come in pairs like that. You can use the same methods we've used to find their eigenvectors, which will also be complex and come in pairs, but we won't discuss that here. You can learn about that more in an advanced course. So we've seen scaled rotations are matrices with complex eigenvalues. Are there any others? As it turns out, in some sense, no. There's a theorem, which we won't prove here, that says all other 2x2 matrices with complex eigenvalues are actually like scaled rotations if you change basis. In other words, if A is a 2x2 matrix with complex eigenvalues, then there's a basis with respect to which the action of A is just like scaled rotation in that basis. For instance, A equals 5 minus 2, 1, 3 has complex eigenvalues 4 plus or minus I. And indeed, A equals P times R times P inverse for some scaled rotation matrix R. That's pretty neat because it means 2x2 matrices with complex eigenvalues really correspond to scaled rotations in the plane warped along certain axes. We now have a geometric picture of what complex eigenvalues mean.